So I decided, thinking about this class and probably what I'm about to do, I should have done day one, all right, before we did anything else, which is just to review a little bit of linear algebra. So I posted my linear algebra notes in course content. There's 300 some odd pages. It's a book. So the next homework will refer to that a little bit, and I'll have you walk through some calculations which are similar to the ones I'm about to show you. All right. So obviously I'm not going to reteach all of linear algebra here tonight, but what I thought I could do with about an hour or so is review the concept of coordinate maps as they appear in linear algebra, and just talk a little bit about, how that works. And then once we're done with this, I'll come back and try to get back on schedule. I'll find something, something to compress. I'll skip some proof somewhere or something, Okay, so let's start at the beginning. Let V be a vector space over R. So what does that mean? That means that V is a set where you can add vectors and you can scalar multiply, right? That's what that means. It's a space which basically allows for vector addition that essentially resembles Rn. And one of the first things we do is we talk about beta, say V1, V2. You can add vectors and you can scale or multiply by numbers. So sometimes a vector space is called a linear space, or in some circles a linear manifold. I'll explain more why that is as we go on here, but definition, beta equal to V1, V2, Vn is a basis for V if what? Number one, what? Beta is linearly independent, right? And two, beta spans V, right? Now, linear independence is, what's that mean? That simply means that C1 V1 plus plus Cn Vn equals to 0 implies that all the constants are 0, right? So if you have a trivial linear combination, it must be the trivial combination. This is a simple way to express the idea that none of the vectors in the basis can be written as a linear combination of any of the other ones, right? They're linearly independent. Spans V, well, that means, for one thing, that means that V is equal to the span of beta, right? And span beta, what is that? That's the set of all linear combinations, right? It's the sum, let's say I equals 1 to n of Ci, Vi, such that, C1 through Cn are real numbers. We also sometimes say a basis is a generating set, right? Furthermore, the dimension of the vector space is equal to the number of vectors in beta, right? Or you could say it's the cardinality of beta. But here, cardinality, just counting, right? In my current nomenclature, the dimension is n, right? So not every vector space has a finite dimension, right? So if there doesn't exist a finite basis for the vector space, it's said to be an infinite dimensional vector space. And in that context, you define, well, you could talk about, you could then start talking about cardinality of the basis and stuff like that, but that's kind of beside that's not for here, all right? So anyway, this is a theorem that the number of vectors in the basis is unique. If you take two different bases for vector space, one of the theorems that you can prove takes a little work, but you can prove that the number of vectors in any basis, if it's finite, it has to be the same. So that makes the concept of dimension well defined, all right? And then, so then what?
The number of vectors in any basis has to be the same. What?
If you pick two different, if you have two different finite sets of vectors, both of which span the vector space, both of which are linearly independent, it has to be that the number of vectors in those two sets are the same. And that number, whatever it is the dimension of the space. There are various ways to argue this. If you look in my notes, basically I construct a matrix by writing one basis in terms of the other, and then I construct a matrix by writing the other basis in terms of the one. And it turns out that these matrices have to multiply to give the identity. But the way they multiply, they give the identity of the number of an n by n identity matrix for the one, and let's a p by p identity matrix for the other. And then because you have that the trace of the product of two matrices commutes, like trace of a times b is trace of b times a, it then follows that they're both equal to the trace of the n by n matrix, or the trace of the p by p identity matrix. The trace of the n by n identity matrix is n. The trace of the p by p identity matrix is p. N equals p. So I have a straight calculational proof of it in my notes. Typically in abstract linear algebra books, you'll find more of kind of like a proof by contradiction. They build up a series of lemmas that says if you have a spanning set for your whole vector space, right? And then you adjoin another vector to it, or a linear combination of vectors that you already have to it, well then that has to be linearly dependent set. And there's some things like this, or if you have, I'm trying to remember. Well, I mean, I'm getting into the weeds here, but you can prove this anyway. Now, then definition. If, right, vector x equal to, say, the sum, I equals 1 to n of x sub I, v sub I, all right? And I'm continuing to use the notation that v1 through vn is a basis. My apologies, that's at odds with the notation we've been using this semester in this course, right? I've been using v upper 1 for components of a vector. I'm now saying that they are vectors. I'm sorry, this is the way I'm wired to talk about linear. It's hard for me to stop. I mean, I could stop now if you want me to. Does it matter? Okay. So here I'm assuming that the x sub i's are numbers, right? These are the components of the vector x. I say phi beta of x equals to x1, x2, xn. And just so you understand me, I also use the notation x sub beta. This is the coordinate vector of x with respect to the beta basis. And the coordinate vector for a specific vector is unique by the linear independence of the basis. All right? And there's another way you could define this. All right? Like this is one definition that you could be given for the coordinate map, right? But equivalently, you could say phi beta of VI equals to EI for all I. Then extend linearly. Now I know your linear algebra course, you proved that if you have a linear map defined on a basis, there's a unique linear extension, right? I mean, if you define a function on a basis, then there's a unique linear map which extends those values to the whole vector space, right? I saw that theorem in your notes. So we could use that theorem to define the coordinate maps if you want, right? And this is actually, this is how I like to think about the coordinate map. It's the coordinate map, what it does is it converts the abstract basis, the abstract ith basis vector to the standard basis. Now here I'm using EI to mean what? 0, 0, 1 in the ith spot, And this notation, by the way, is my sneaky column, hidden column notation. So when I write like this, that's a column vector. If I want to write a row, I'll put square brackets. So that's the coordinate map. Now, I also like to draw a picture of this. Basically is this. Here's my abstract vector space, V up here, right? And down here is my copy of Rn. The coordinate map goes like this. And it takes like an abstract vector up here, V1, and it maps it down here to the standard basis element E1, just like that. Let's look at an example.
Can you explain what you saw in our notes? Linear algebra again, that we do something to a basis.
Oh, theorem. Yeah, there's a theorem. If S of VI is equal to WI for all I, 1 to n, where V1 through Vn, let's say, is basis for vector space V, and W1 through Wn are elements of W, a second vector space. All right. Then there exists a unique T from V to W linear, a linear map such that T restricted to the basis beta, I'm going to call that beta again, okay? T restricted to beta gives me back the initial mapping S once more. In other words, if you fix the action of a potential function on the basis, there is a unique linear map which extends that to the whole set. If you tell me how the linear map acts on the basis, you've told me how it acts everywhere. It's a linearly independent spanning set for a vector space. So it could be many, many things. let me put this into practice to show you what I mean. So if you're not, totally comfortable with that theorem, I think it's good to look at an example. Yeah? So typical examples of vector spaces, what are they? If you don't mind, I'm going to erase a little snippet of that theorem. Is that okay? Just for the sake of it's bothering me. So examples. We could have V equal to, well, for example, obviously Rn is a vector space, right? We can do matrices. You could also do complex matrices, right? Still a real vector space. You could do polynomials. Right? You could do polynomials of, say, order n with coefficients from R. Also a vector space, right? Solution sets to differential equations form vector spaces. Homogeneous differential equations. That's a nice example of a vector space. You could do things like polynomials in two variables, also a vector space. A very interesting example of a vector space is if you say L of VW equal to T from V to W such that T linear. In other words, this is the set of linear transformations from a vector space V to a vector space W. This is, again, also a vector space because you can add two linear transformations and still get a linear transformation. You can scalar multiply a linear transformation and still get a linear transformation. So this is also, yet again, a vector space. All right? Now, the basis for each one of these things is rather different looking, right? Let's see here. I'm going to do polynomials. So let's look at P3 of R, right? So a typical thing in there looks like what? Something like ax cubed plus bx squared plus cx plus d, right? That's a typical cubic polynomial, possibly degenerate. They all could be 0, right? Like the leading coefficient doesn't have to be non-zero. So technically speaking, these cubic, instead of cubic polynomials, we should say degenerate cubic polynomials because if that leading coefficient's not 0, it's not really a cubic, right? Anyway, so this basis, beta, you got basis, you can, the other thing about the basis is it's ordered, okay? So I would do this though, x cubed, x squared, x and 1, right? If this above is f of x, what's the coordinate vector of f of x? Mm-hmm.
So it would stay the same, except it would just be x cubed, x squared, x plus 1.
No, there's no x's. See, the coordinate vector is a element of Rn. So if I ask what the coordinate vector is of an abstract vector, the answer should always be a concrete vector in Rn, a column vector. Ones? Well, A, B, C, D here are numbers. They're just, that's the answer. A, B, C, D is the answer here. because to form f of x by a linear combination of the basis, the weights for the linear combination are respectively a for x cubed, b for x squared, c for x, and d for 1. I mean, there's 1 here, you know.
Yeah.
In contrast, if I had gamma equal to, say, 1x, x cubed, x squared, because I wanted to be weird, all right, we could ask, what's the coordinate vector of f of x with respect to gamma? And if we did that, it would be somewhat different looking. See, a basis is an ordered set. The order matters. So 1 comes first. What's the coefficient of 1 in the linear combination?
Oh, no, it'd be D.
Mm-hmm. Be D.
Okay. Oh, yeah, okay.
Yeah.
C,
Yeah.
A, and B.
Very good. Yeah.
So we have a function and the basis is
The coordinate map, the coordinate map trades the abstract vector for the corresponding column vector of coordinates of the vector. And those are unique because the basis is independent. Right?
So for this one, is there a finite set of bases?
Oh, no. There are infinitely many bases possible for P3.
Well, even in relation to this f of x?
The basis doesn't, f of x doesn't depend, I mean, what do you mean? The choice of basis, we could do lots of other things. Like, you could, I mean, in addition to just reordering them, you could do things like add, you know? Or here's another basis for P3. Alpha, beta, I'll use delta. You could do this. Delta is 1, x minus 1, x minus 1 squared, x minus 1 cubed. This is an...
They all follow the same pattern.
Well, they don't have to. I was doing that because this one's easy. And I'll show you why in just a second here. That one's, yeah?
Can you show us one without a pattern?
Can I show you one without a pattern? Yeah, perhaps, but remember this, f of x is what? Taylor's theorem says what? It's the sum, let's say j equals 0 to infinity of the jth derivative evaluated at 1 over j factorial times x minus 1 to the power j, right? Taylor's theorem. So, yeah. So this is a cubic poly. I mean, here f of x, I'm still working on this one. It's cubic. So all you're going to have is, you're going to have f of 1 plus, let me write it down here. You're going to have f of 1 plus f prime of 1 times x minus 1 plus f prime prime of 1 over 2 times x minus 1 squared plus f prime 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 of 1 over 6, because 3 factorial is 6, times x minus 1 cubed. And that's where the series truncates, because fourth derivatives and higher are 0 for a cubic polynomial. But my point to you is that these numbers are kind of ugly. Well, they're not super ugly, but what's like f prime of x is what?
3x squared, 2x.
Oh, we need the a though, right? So 3ax squared f prime prime. All right, 6ax plus 2b f prime prime prime. 6a, and then of course higher derivative 0. So check it out. F of x is equal to f of 1 is what? A plus b plus c plus d. What's f prime of 1? Well, 3a plus 2b plus c. The reason I chose 1 is that the evaluations are super easy if I do that. Just makes my life a little less complicated this time of night. And then plus 1/2 what? F prime prime of 1, which was 6a plus 2b times x minus 1 squared. And then plus 1/6 what? Times, yeah, 6a times x minus 1 cubed. So what's the coordinates of f with respect to the delta basis?
That first chunk, a plus b plus c, and then 3a plus 2b plus c.
So you said, so the 1 is the first one, so it's a plus b plus c.
Oh, and then, yeah, well, that one's in order, so yeah.
Yeah.
3a plus,
So this was not completely random as the feature request that you put in a couple minutes ago. So 3a plus b, yeah. And of course a for the last one.
so you can just make the basis whatever.
Yeah, because you could replace 1 with any number you like.
Which one?
Like the number 1 in this part of the example, I could just as well have put any real number here and looked at the Taylor expansion with respect to any real number, and then I can shift the basis, the standard. Sometimes this is called the quote-unquote standard basis for polynomials. I try not to. When I say standard basis, I'm thinking of column vectors. All right, but yeah. But okay, so I wanted to show you that if we define the action of a linear transformation on the basis, that uniquely defines the linear transformation, right? So let me make good on that. Sure. Oh no, because Taylor's theorem is based on numbers, right? Numbers.
And so we can also, as long as it's a polynomial, that basis won't change, right? You have to have a 1x, a squared, and a cube term. And you can do whatever you want with those terms, call it a basis. But it has to follow that pattern.
Well, you do have to have 4 linearly independent
Yeah.
polynomials. So, like, there's going to have to be a cube in there somewhere.
Yeah.
There's no way you can recover a cube unless you have one to start with, right? Like, you're just adding and multiplying by real numbers. So, you can't do anything, but you can do a lot of things. Yeah. Oh, 6 over 2 is 3, and 2 over 2 is 1, and over, yeah. Incident.
So there are some parameters of what you can do, but you can do a lot still.
There, yes, but there are infinitely many choices of bases for P3R, but all of them have 4 vectors that are linearly independent. That is common. That's not up for grabs. Now, I'm going to define a linear transformation using that theorem. And then you're going to tell me what the linear transformation is. So here's the linear transformation. T of 1 is 0. T of x is 1. T of x squared is 2x. And T of x cubed is 3x squared. The theorem says, since I've defined the linear transformation on a basis for P3 that uniquely allows us to extend to a linear transformation on the whole of P3. So if I tell you T of, say, A plus bx plus cx squared plus dx cubed, you can tell me what it is, right? So a times t of 1, right? So it's a times t of 1 plus b times t of x, right? Plus c times t of x squared plus d times t of x cubed. Sorry, I got kind of small there, but that's, just like you said, that's 0. That's 1. So we get b plus 2cx plus 3dx squared. Tell me the name of the mystery contestant. What is this linear map? The derivative, right? Okay. So I hope that wets our whistle here. I mean, it gets us started. Let's bump it up a notch. Es bueno. That's good. Actually, I think this over here I can now do without. Now, I've shown you some of this stuff already, Audric, but I need to share it with them as well. Okay, so the matrix stuff on column vectors has some particularly nice technology. So in particular, definition, I say L, let A be an element of R m by n. Then L sub A is a mapping from Rn to Rm given by L sub A of x equals to Ax for all x in Rn. I call L sub A the linear transformation induced by A, or linear map induced by A. Now, what's our usual? Maybe you've seen this other notation. A popular notation for L sub A and A, as they're related to each other, is to talk about the standard matrix of the map, right? So, in particular, the standard matrix of L sub A is A. Right? But I can be more specific. This is also equal to, you know, AE1, AE2, AEN, right? Because the ith column of A is A times EI, right? And so this is also L of E1, rather L sub A of E1, L sub A of E2, L sub A of EN. But if you like, I can make yet another definition for T, an element of the linear maps from Rn to Rm, the standard matrix of T is denoted like so, and it's given by T T acting on E1 all the way out to T acting on En, right? This is a m by n matrix. And I never moved the chalkboard back. I never moved my camera back, did I? Dummy. Sorry about that, guys. Right? Now, can you tell me, what things do we know about the standard matrix? So here's some fun facts. But before I write any more, let me just give you guys a chance to catch up. Any questions? This one? So if we have a linear mapping, like a map from Rn to Rm, then we can define a matrix corresponding to that map, which we call the standard matrix. It's an m by n matrix, and its columns are formed by the linear map acting on the standard basis, like E1 all the way out through En. This L sub A notation is another way to get at it. The mapping induced by A I call L sub A. So the relation between the standard matrix notation and the L sub A notation is just that the standard matrix of L sub A is literally just A itself. And this corresponds naturally to this notation because, like, if you bust out A into its columns, column 1 of A is AE1, but that's also L sub A acting on E1. So this world and that world, these are two different notations to get at the same idea. But the standard matrix plays very nicely with things we can do to linear maps. For example, we can take a scalar multiple of a linear map, and guess what? It's the same as the standard matrix of the linear multiple is the linear multiple of the standard matrix. It's kind of a small thing, but that's true. If you could add two maps, say T1 and T2, the standard matrix of the sum is the sum of the standard matrices. If the matrix is invertible, something nice happens. But suppose we have two that we can compose. This is really the big one. If we have two linear maps, S and T, which are composable, right? The standard matrix of the composite of two maps is, in fact, the product, the matrix multiplication of the standard matrices of those two maps. Many would argue that we define matrix multiplication precisely so that the equation I'm writing right now happens. Here we have composition of linear maps. Over here, we have multiplication of matrices. But they equal each other, indeed. And so, incidentally, the standard matrix of the identity map, right? If we look at the identity map on Rn, then the identity map has standard matrix I sub n, the n by n identity matrix. And you put these two things together, basically these quickly give us that if a matrix is invertible, the standard matrix of the inverse is, guess what? The inverse of the standard matrix. I had to use that to do one of the homework problems you guys had in like mission 4 or 5, because I found myself finding the inverse of a mapping. It was a linear map, and I used this for my solution. Yeah. Yeah. Let's look at let's actually do this proof, yeah? If I can find.
What's the last fun factor there?
Oh, so the standard matrix of the identity map on Rn is the n by n identity matrix.
Okay.
the standard matrix of the identity map is the identity matrix. So, so check this out. So S composed with T, right? Acting on EI, I'll say EJ actually. What is that? By definition, this is S of T of EJ, right? But by definition of standard matrix, that is the standard matrix of S times that vector, whatever that is, right? But what's T of EJ? Well, it's the standard matrix of T times EJ, by definition of standard matrix. S and T are linear maps here. So like S would be, say, from Rn to Rm, and T would be from, I guess, I need to make it composable, let's say Rp to Rn. So that makes S a m by n. It makes T a n by p. So they can be multiplied, right?
I thought, n by p, wait, why is it n by p? Because you said it's from p to rn.
That's right, but the letters switch. See, this is from Rn to Rm, but it gives us an m by n matrix. M as in mommy, n as in nanu nanu.
Okay, and so those are multiplied.
Yeah,
Yeah.
yeah.
Column by vector or by row. And so my question is, can you multiply S and T? Can that equal, like S composed with T of EJ, can that also equal the matrix S times the matrix T of EJ?
I mean, it is. That's what this calculation shows. Yeah. But take a step back here for a second. The definition of the standard matrix of a map is what? Like notice that column J of the standard matrix of S composed with T is what? It is S composed with T, right? Acting on what? EJ. But by this calculation right here, it's also equal to what? It's equal to the matrix of S times the matrix of T times EJ. But guess what? When we have a matrix times the jth standard basis element, that gives us the jth column of that matrix. So this is also column J of the standard matrix of S times the standard matrix of T. But that shows that so since these two matrices have the same jth column, and J is arbitrary, it follows that these two matrices are equal. Right here. Column J of this is equal to column J of that. The thing I keep using that'll slip past you if you don't watch out for it is that if I have a matrix M, right, whatever it is, and I multiply it by EJ, that is column J of M. This fundamental truth about matrix multiplication is key to many proofs if we use this system of notation.
And EJ is just whatever column that you choose?
Yeah, I mean, just pick J to be arbitrary, but EJ is the standard basis element that's got 1 in the jth component and zeros elsewhere. Yeah, yeah. Okay, so if we have a linear transformation from column vectors to column vectors, it's pretty easy to understand. We just have to find the standard matrix. You find the standard matrix, you've described the transformation, right? And then we have all kinds of like beautiful, simple theorems about whether the map is invertible, or whether it's onto, whether it's one-to-one, you know. We can use the column space and the null space of the matrix to basically capture those things. If the null space of the matrix is trivial, the mapping is one-to-one. If the column space of the matrix is equal to like Rm, then the mapping's onto, right? So, and we have something called the rank nullity theorem. The rank nullity theorem says that the, let me write it over here. What does rank nullity theorem say? So if A, this is the matrix version of it. If A is an m by n matrix, and the null space of A is x in Rn such that Ax equals to 0, right? So the null space of the matrix is the set of vectors which are sent to 0 by the matrix, right? So is that empty? It's never empty, right? There's always at least one vector in there, which is what? Exactly, 0 is always in there. So that's the null space. And the column space is nothing more than the span of the columns of A. All right, then here's rank nullity theorem. N is equal to the dimension of the column space of A. Well, I'll write the null space to start with. Dimension of the null space of A plus the dimension, it doesn't matter which one you write first. I don't know, whatever. So the dimension of the column space is called the rank of the matrix. The dimension of the null space is called the nullity of the matrix. So rank plus nullity is the number of columns. The proof of this is essentially just Gaussian elimination. You can take a matrix, you row reduce it. The number of non-pivot columns corresponds to the number of free variables in your null solution. Each free variable you get in the homogeneous solution corresponds to a vector in the null basis. We saw this calculation when you were calculating the perp, looking at the null space of the transpose of the vectors. That was a null space basis calculation. Rank is literally the number of pivot columns in the row reduction. So this theorem is really stupid if you think of it in those terms, right? It says that the number of columns plus the number of pivot columns plus the number of non-pivot columns is equal to the total number of columns in the matrix. Well, why is this a theorem, right? And yet it is a theorem, and trust me, many people who have earned A's in linear algebra do not know this a year after taking linear algebra, in my experience. Well, maybe not A's. Not A's, let's say B's. A students usually lock on to this one longer. But okay, so that's the big story about linear transformations on Rn. How about linear transformations from abstract vector spaces to abstract vector spaces? Like that one, differentiation, right? So here's the deal. I'm gonna make a picture. Suppose we have V with basis beta, all right? And I'm going to suppose beta is, again, V1 through Vn. And then we've got some abstract, linear transformation. I'm going to call it T. All right? And it goes over to another vector space, W. And I'm going to use gamma for the basis over there. All right? And I'm going to denote the basis in gamma by W's. W1, W2. Let's say it's M. M as in mommy. So I'm going from an n-dimensional space to an m-dimensional space again, all right? But this time, not necessarily column vectors, all right? These could be polynomials, they could be matrices, they could be any number of things. Okay, so then, in this context, we have two coordinate maps to work with. We've got the beta coordinate map from V, right? That goes down here to Rn. And we've got the gamma coordinate map over here. It goes down to a copy of Rm. All right? So in this context, we can define a corresponding linear map down here. Let's call it linear map induced by the matrix bracket T, and I use the notation beta gamma. So I mean, we can multiply by, and so this is really, this picture I'm giving you as a definition in some sense. I mean, this picture for me essentially defines the matrix of an abstract linear transformation with respect to bases beta and gamma. Let me give you an equation which perhaps is a more proper definition. So what I'm saying, right, is that we could track a vector upstairs, let's say x, right? Over here, you'd have what? You'd have t of x, right? So that gives you, down here, it gives you x sub beta, the coordinate vector of x with respect to the beta basis. On the other hand, over there, I have the coordinate vector of tx with respect to the gamma basis. The matrix of T with respect to this pair of bases is the matrix which is needed to multiply from this guy to that guy. In other words, if I multiply by T beta gamma, that gives me essentially the definition of T beta gamma implicitly. I could write it, let me write it down again. T beta gamma is matrix for which the coordinate vector of T of x gamma is equal to this matrix times the coordinate vector of x beta for all x in V. Now, that definition at first glance doesn't seem to be that convenient or useful. Maybe you'd like a formula for the standard, for the matrix T beta gamma. Can you guys tell me how to get a formula for it? How about this? What is the coordinate vector? What's the coordinate vector of Vj? Hmm. Yeah, let's see here. It's 0 times v1, right? 1 times vj, right? 0 times vn. So what's the coordinate vector? It's zeros, a 1 in the jth spot, and zeros again, right? What is that? That is EJ. The coordinate vector of the jth abstract basis element is the jth standard basis element. The coordinate map is a machine to convert the abstract basis to the standard basis, is the way to think of it. Now, the reason that's interesting is that means that if we take the case x equals to vj, see what happens to this equation up here? The matrix of T of vj with respect to the gamma basis is equal to matrix T beta gamma times what? Times the coordinate vector of EJ, which is what? It's EJ, right? But what is that? Remember, any matrix times EJ is the jth column of the matrix, right? So this is column J of this matrix I'm trying to describe. Oh, so there you go. That's a formula for the matrix. So another definition you could give is that the matrix T beta gamma, it is a matrix made up of coordinate vectors of the images of the basis of the domain. It's like T of V1 with respect to gamma, T of V2 with respect to gamma, T of Vn with respect to gamma. So I mean, the advantage of what I just wrote is it makes you feel better about a definition because it gives you an explicit definition for the matrix, right? But I find in practice that the implicit definition is actually more convenient for actually finding these matrices for specific examples. So like, let's use what's in the corner here to write down the abstract matrix of that derivative map, right? We could do it, right? See this here? Let's use this up here. Let's say beta is equal to 1x squared x cubed. And let's let gamma, we'll let it be 1x and x squared for P2, right? So if we use the orange boxed idea, the matrix of T beta gamma is equal to, let's see here, I'm supposed to find the gamma coordinate vector of T of V1. I'm going to run out of space here. If you don't mind, I'm going to write it, I'm just going to write 0 here. So like